Welcome. This is again the week 5 and my second lecture of week 5, that is lecture number 22 is I will talk about the blast furnace product and their utilization. And the major concept that will be cleared here is the hot metal composition and its control, and blast furnace slag and its usage, and the blast furnace gas and its usage. Okay. Now, typical hot metal composition, if you see, and I am just comparing the Indian hot metal with some other international hot metal, other countries like Japan, Europe, USA and Indian composition. So, if you see the carbon percentage is usually same in all the hot metal from Japan, Europe, USA and India. If you consider, that is the carbon percentage varies from 4 to 4% and it is more likely because the liquid steel is saturated with the carbon under blast furnace condition. Okay. So, it is will be around 4 to 4.5. Now, silicon if you consider, then you can find a variation also, and we have very high silicon. Our steel, it may be 0.7 to 1.3 weight percent of silicon, compared to Japan it is 0.3 to 0.45, Europe 0.3 to 45 and USA 0.4 to 0.7. So, compared to other countries, okay, you can find in India we have a large silicon, and it is mainly because of our source. It is we have iron ore that contains lot of silicon. Beside, we have coke ash. Coke ash is also another source of silicon that also contain lot of silicon. Okay, coke ash also silica is there, a lot of, and we have very high ash content in coal, even in coking coal, as I said, and these account for this very high silicon into the hot metal. And another thing I will talk about, that is under very basic condition you can reduce the silicon to also to a great extent, but under the slag of Indian condition, which contain lot of alumina, the slag remain viscous and you cannot increase the basicity also, because the operating window for the blast furnace slag in India is very small pocket. I will show you. So, as a result, you cannot increase the basicity beyond 1. Okay. So, if you increase the basicity, then you can reduce the activity of silica in the slag, and then you can move the reaction in the forward direction to some extent. That is also. So, I will discuss about all these things in detail, but you can note that is the silicon is quite high, and manganese 0.2 to 0.4, and it is varying little, 0.2 to 0.65, 0.5 to 0.5, and in India we have quite less, 0.04 to 0.1. Our manganese is quite less because the ore do not contains too much of manganese, or possibly we are not recycling the BF slag for the sinter making, and then that could be another source. So, I will talk about that. Manganese we are okay. And if you consider the phosphorus, European steel you have a very high phosphorus, you can find 0.06 to 1.5, and that may be they are working with the ore which is the very high phosphorus content. That is why they have special technique for removing those phosphorus. Either they make a double slag practice, or they use the lime powder, that is called the LDSC, along with the oxygen blowing, they use also the lime powder, that is called the LDSC. Some separate technique is there to take care of this very high phosphorus, also double slag practice, because large volume of slag will be there, difficult to handle. Otherwise, you can see Japan has a very low phosphorus, up to 0.095 to 0.1, because their ore is very good with respect to the phosphorus. That is, the phosphorus content of the ore is less, and also in USA also very less. Only in Europe it is very high, and India it is intermediate, 0.1 to 0.3. So, we have also some special technique. We basically control it by the blowing practice rather than using the lime powder. We use it by blowing practice because our phosphorus is not that high. We can maintain it 0.1 to 0.3, but here is a special technique is there. And sulfur, if you consider, we are also 0.05 to 0.08, okay, and it is quite less in case of the Japan, Europe as well as in the USA, and we are little on the higher side, because as I said, we also cannot maintain because sulfur is removed under high basic condition, but in the blast furnace slag we have limitation of increasing the basicity beyond 1.1 or 1.12. That is a real problem in our case, because we have alumina in the slag that makes it viscous, and also with alumina you cannot increase the lime to great extent, because in that case slag liquidus increases. So this is the thing, that is the iron ore coke contains slag. So these are the thing, special blowing practice is required here, and in this case, so okay. Now the source and partitioning of the impurities. About 60% of silica in our ore, that is in our hot metal, comes from the iron ore feed, rest from the coke ash, 40% from the coke ash. So coke ash also quite responsible for the silicon in hot metal. Over 85% of the total silica is transferred to the slag, and 15% get reduced and come report to the hot metal. So we are being able to take out the 85%, but still 15% come into the hot metal, that is responsible for the silicon. And then coke is also the major source of sulfur. If you consider the sulfur, then coke is the major source. 90% of the sulfur in the hot metals come from the coke, sulfur in the coke. And over 90% of the sulfur is removed to the slag, because it is a highly reducing condition in the blast furnace. So you can remove the sulfur significantly, 90%, okay, and remainder reports to the hot metal. But what I was telling, that still our sulfur is 0.05 onwards, 0.05 to 0.08, little higher, in spite of the fact that sulfur content in the coke ash also quite less. Our ash content in the ash, sulfur is less, but still we have very high sulfur into the hot metal compared to Japan and all these things, because we have some limitation in the slag basicity, as I said, because although we remove the 90% sulfur into the slag, but we can remove further more 95% if our slag is more basic, and we can have low sulfur into the hot metal. Okay, so that is the way. And 60 to 70% phosphorus comes from the iron ore, right? Rest from the coke ash. If BF slag is partially used as a sinter making, then the phosphorus will come more, because sometimes there is a BF slag, as we will see later on, there is the LD slag or the steel making slag as a very less utility. You cannot convert it to a cement making purpose, unlike the blast furnace slag. So BF slag is a problem everywhere, and people try to use this BF slag in different applications. So if it could be used for the sinter making also, because BF slag also contained around 20% iron oxide, so not bad. So but it is associated with the P2O5 and then CO and all these things are there. So as a result, it is also used into the sinter making some countries, and if you use the BF slag, then that will give some input to the phosphorus, and we are not doing that thing. Percentage phosphorus in the Indian hot metal may be 0.4, as I said, 0.3 up to 0.4, which is much higher than the Japan hot metal and much lower than European hot metal, because European hot metal, they have lot of phosphorus is coming basically from the ore. They have a very high phosphorus grade ore. From there they are extracting the hot metal, so their phosphorus is coming to the hot metal very high. That's why they have some separate technique, either lime powder injection with the oxygen glancing, and also the double slag practice they will take to take care of this very high phosphorus. But India, we have phosphorus in the intermediate range. So what we do, we have a special blowing technique in the steel making that will come later on. And almost all the phosphorus reports to the hot metal, because 100% P2O5 is converted to phosphorus and reports to the hot metal, right? So this is the partitioning, you can understand. There is a source and partitioning of different impurities. And major source of manganese could be the BF slag if it is partially used into the sinter mix, as I said. But the coke is also another source of manganese. 90% manganese is partitioned into the hot metal, right? So iron ore also it comes, iron ore, through iron ore manganese oxide come, but not much. Coke is also another source, but major source could be if some amount of BF slag is used into the sinter mix, okay. And 90% manganese is partitioned into the hot metal. So 90% manganese comes to the hot metal. It doesn't go too much of slag, because manganese oxide is a basic oxide. So it is not very comfortable to remain into the slag, okay, basic slag. So manganese is mostly partitioned into the hot metal. Fortunately, our ore do not contain too much of MnO. Now let us consider the mechanism of silicon transfer in the hot metal. How the silicon is transferred into the hot metal. If you see, now first you can see some first silica in the coke ash burns at raceway to produce the SiO gas. You can find this is the raceway. In the raceway, coke ash is there, and the coke ash contain SiO2. SiO2 from the coke ash reacts with the carbon at high temperature is formed the SiO gas and the CO gas. You can see right hand side both are gas. So this reaction is very fast, and also temperature is very high. So this gas is formed, and when this SiO gas move up through the dripping zone, then some reaction take place. SiO gas react with the dissolved carbon, okay, and forming silicon and CO gas. And also SiO gas can directly be decomposed, okay, directly be decomposed into SiO2 and Si. SiO gas can be decomposed to Si2 and Si like this, twice SiO, forming SiO2 plus Si, or it can react with the dissolved carbon into the hot metal, and then it can form silicon and CO gas, and then silicon will go into the hot metal, that is the hot metal. It may be oxidized also, SiO2 na, SiO gas may be oxidized to SiO2 also by FeO reduction, because FeO can be reduced, right? FeO plus SiO2, FeO can be reduced to iron, and the silica SiO gas may be oxidized to SiO2. This can also happen, because when through the dipping zone, whatever the FeO is left out, that will be reduced, because it is a huge reducing atmosphere. So SiO2 besides your FeO is less stable compared to the SiO2. So as a result, FeO will get reduced immediately by silicon gas, SiO gas, and SiO gas will be oxidized to SiO2. Now final silicon partitioning is done at the slag metal interface here, and finally when the slag comes, and final slag basically form here, this is the hard slag, and here the final partitioning take place, hot metal and the slag, final partitioning take place there. And this reaction, final partitioning, basically is SiO2 plus twice C forming Si plus twice CO, okay. And if you have a basic slag, then SiO2 activity will also be reduced, right, okay. So this is the thing, this is the way the silicon basically transferred into the hot metal. You can find the silicon control, very important in the hot metal. How you can control the silicon in the hot metal? First is the low adiabatic flame temperature. How does it help? Because if you see consider this reaction, silicon reacting with the oxygen forming the silicon oxide, it is a highly exothermic reaction. That is, it is characterized by minus delta HR, heat of reaction. So it is an exothermic reaction. So that means heat is generated in this reaction. So if you reduce the temperature of the atmosphere, this reaction will be move in the forward direction. That happens. So if you have a low ratio adiabatic flame temperature, then this reaction will move in the forward direction. That means silicon will be oxidized to silica and go into the slag. So as a result, there is the hot metal silicon will reduce. Hot metal silicon will reduce. So that is the one thing. So if you reduce the hot metal temperature or the wrapped, you can reduce the silicon into the hot metal. Or if you increase the hot metal temperature, or if your wrapped is increased, then your silicon in the hot metal will increase, because simple of law of mass action, that is you can see it is an exothermic reaction. Always this reaction will favored at low temperature. If you increase the temperature, then reaction will move in the backward direction. As a result, silicon in the hot metal will increase. High top pressure, you can see here from this reaction, you have a gas on the left hand side, right hand side solid, okay. So this gas is entropy, that is you can find. So your silicon reacting with the oxygen gas forming the SiO2, that is solid. So if you give a high top pressure, if you increase the pressure in the system, then this reaction will move in the forward direction, because you are increasing the partial pressure of oxygen by increasing the pressure. As a result, the reactant oxygen activity will increase. So this reaction will move in the forward direction. As a result, your silicon from the metal will be oxidized to the silica. So as a result, you will have a less silicon into the hot metal. That is, high top pressure basically facilitate towards that. Do you get that? That is the high top pressure. Slag basicity. If you increase the basicity, what happens? This silica into the slag will react with the, suppose basicity means lime you are adding, it will form tricalcium silicate with the lime. So, where the activity of SiO2 is very low. Okay, so by adding flux you can reduce the activity of SiO2 low. So, this reaction will move in the forward direction. So, obviously your silicon in the hot metal will reduce. So, that is the high basicity, and some you can see some data also from the plant. If you see the percentage of silicon in the hot metal and you are increasing the basicity, then you can see silicon percentage decreases progressively. So, as I said, lime forms a strong compound with silica reduces activity, that is the reason. So, if you want to control the hot silicon into the hot metal, basically you have to reduce the hot metal temperature or wrapped. Second thing is that you can use the height of pressure, or you can use a very high basicity of slag. But unfortunately, with alumina, we Indian slag, we Indian blast furnace, the slag contain a lot of alumina. So, it is a viscous slag and you cannot make it too much of limey. If you make it lime, and you have a very narrow operating window for the slag composition. So, in that case you cannot make the slag very basic. Mechanism of sulfur transfer in the blast furnace, you can see how that sulfur get transferred. Here also in the raceway, your coke axe can react with the SiO gas just generated, it form the SiS gas plus CO, or the iron sulfide in the coke ash, FeS in the coke ash can react with the SiO gas and the carbon forming SiS gas, CO and iron. And in the Bosch, when the gas move up, would the cis gas move up through the Bosch and belly, then cis gas can decompose to silicon and sulfur. And finally, in the heart, this reaction can take place. The CO in the slag can react with the dissolved sulfur and carbon, forming the calcium sulfide and the CO gas, right. So, this is the final partitioning of the sulfur in the metal and slag. And if you see the composition, how it varies, above the taphole, this height above the taphole, this is the taphole, and above the taphole if you see. So, you can say this is the 12 line, basically here is the 12 line. So, you can see the sulfur in the hot metal increases because in the Bosch and belly region the increase is very high because of cis gas decomposition. So, cis gas decomposition, so sulfur is increasing here, and then this is basically in the metal sulfur increases. And then for metal sulfur again it decreases, because here basically in the heart there is a slag metal reaction take place. In this slag metal reaction, very strong reaction, and because calcium oxide in presence of calcium, because the calcium in this region, the calcium in the slag is quite less up to the 12 region, not 12, but here the calcium, because calcium dissolution requires a lot of FeO, or it requires little higher temperature for calcium to dissolve into the slag. As you will see, the slag calcium does not dissolve too much. Basically here below the 12 you have a lot of calcium into the slag, and that basically reduces the sulfur to calcium sulfide and forms the CO gas. And because of slag metal reaction, sulfur again decreases. And in this case of slag also you can find from top, sulfur in the slag also increases, okay, and then because of slag metal reaction again it increases into the slag. Slag metal reaction is taking place where the sulfur is going to the slag. Sulfur control, if you see, that is this is the overall reaction on the slag metal reaction, how you can control the sulfur. Basically major partitioning of the sulfur take place by the slag metal reaction, and it is a very favorable reaction for desulfurization under blast furnace condition, reducing condition. You can see the right hand side CO gas, it moves away. So, this reaction moves in the forward direction, and so reducing condition is the first, because as you can see the carbon react with the oxygen and forming the CO gas, which is very stable at high temperature. So, it goes away, and this calcium basically attacks the sulfur and forming the calcium sulfide and joins the slag. And then high basicity, obviously if your basicity is high, there is the constant, as the activity of CO increases, this reaction will move in the forward direction. More the basicity, more you will be able to remove the sulfur, okay, but I have a limitation. And then Indian blast furnace operate with the low basicity to maintain the fluid Bosch slag. That is the very important. We cannot increase the basicity too high because of alumina content. I am repeating this thing. And the low sulfur in the coke ash, becomes helpful, because you can see the low sulfur in the coke ash. Coke ash contain only 0.6% in the Indian coking coal compared to others. Coke ash sulfur content in our coking coal, only good thing is that sulfur content in the coking coal is less, only 0.6%. So sulfur coming from the coke ash, there is a 90% sulfur from the coke ash, but two, that is there, the sulfur percentage is not very high. That is the good thing, because we cannot play with the slag basicity in the blast furnace such that we can remove the sulfur. So it is basically helpful because we have less sulfur that is coming from the coke ash, and we can maintain with the 0.05 to 0.08. Evolution of the blast furnace slag, if you see, first there is the primary slag formation. So what happens when you are reducing higher oxide reduced to woostite in the upper part of the furnace, then woostite can combine with the amino, there is a gang into the iron ore, that is like mostly the amino, SiO2, and can make some feasible eutectics, and with and without the lime. Basically then in the upper part of the furnace, lime cannot dissolve into the slag too much. They are basically Fu, amino, SiO2, this system, they basically make some eutectic, some slags formation, that is called the primary slag. And this primary slag, as it goes down, because Fu progressively decreases because of direct reduction, as a result the slag become again very viscous in absence of lime, right? So you have Al2O3, you have SiO2, MnO, and Fu is decreasing, the slag become viscous. So primary slag, as it goes down, become little viscous, and then you form, so you can find this region, this is the Fu, Al2O3, SiO2 system is there. In this system, that is the Fu is there, this is the Fu percentage. So as you are going down, this here the slag Fu percentage is less, and these two line you can find, there is line A and the line B. Along the line A, for a particular Fu, so if you consider for a particular Fu, SiO2 by Al2O3 ratio is quite high, 3 to 4, okay. So, and it is, you can find it is the very low melting eutectic, 1200 degrees centigrade. Here it is 1700 line, so you can find it is passing through it, and then again it is 1700 like this, so it is passing. So if the silica to alumina ratio is high, then you can have little fusion temperature is less compared to B. If you consider the B, here basically SiO2 by Al2 ratio is very low at a particular Fu ratio, any point. So here basically is the iso SiO2 Al2O3 line. So here iso SiO2 Al3 line, this composition is less, here it is very high, okay. It is little fluid, A slag is little fluid, and B is very viscous, right, okay. Now then we form the boss slag. What happens as soon as the slag reaches the boss, because of high temperature, now lime start dissolving. Now we are coming to a system, Fu, Al2O3, SiO2 system to, we are coming to Al2O3, SiO2 and CO system, because CO now dissolving into the slag. And as CO is dissolving, you can find the liquidus of B also is decreasing, lying this line, along this line and coming here. And here also, if you consider that slag A also with the lime addition, its that is the fusion temperature is also decreasing, it is coming to this thing. So you can send 1500 line, 1400 line, then this line. So they are crossing and coming here. Here basically, here what you find finally, it is a very, this zone, all of them are coming in this zone, and this is a very fluid slag, and its liquidus is quite low, 1300 to 1400 degrees centigrade. And this is the range where the blast furnace, our hard slag also finally form. When the hard slag form by absorbing the coke ash that is released in the tuer, as well as more lime, because at high temperature lime. So finally we get to this composition, that is the hard slag composition, and this is the composition we have to operate the blast furnace. And in this case what happens, if you see the alumina content is given by this, and in alumina content in this region is around 10 to 20%, 10 to 20% alumina is there in this region, and you have CO by SiO2 ratio, if you see in this region, it is around 1.12, 1.1, around 1, of the order of 1. So if we now increase the more lime, this the lime line is this, if you have in this region, lime is high, so is liquidus is high. So more limey you cannot have. So lime usually 50% and silica is around 50%. So that is the best ratio, not 50% because other constituents are there. So what I am saying, 1:1 ratio. So here the basicity is 1. So this is the hard slag. Finally, you are coming to this slag. So this is the way it evolves. First, you have a very viscous slag, and then primary slag form, and then primary slag either can move this way or can move this way. If it moves with a very high silica to SiO2 ratio, it is little liquidous, and here you can find as it goes down, FeO content is decreasing progressively, and so as the FeO content decreases, is basically liquidus is increasing. So you can find here it is liquidus is increasing this way also, but A is little fluid, B is little viscous, because A in this case the SiO2 to L2O3 ratio around 3 to 4, here it is around of the order of 0.5 or something like that. So now when it comes here, basically almost no FeO is there. Now CO is dissolving into the system is becoming L2O3, SiO2 and CO, and then also its liquidus is decreasing and coming this way, and A also coming this way, and finally in the hard slag forms, after absorbing the coke ash as well as the mole lime, you have this composition. So I have to maintain within this composition in the blast furnace. So operating window of the slag is quite less. So we cannot increase the basicity. Here the basicity is of the order of 1. So if you see the major constituents of the blast furnace slag, CO is around 30 to 36%, SiO2 28 to 32%, and here the basicity lies between 1 to 1.13, and L2O3 is around 18 to 22%, and MgO 9 to 12%. Right. So MgO is basically additionally added sometimes to make the slag fluid, and we do it, but there is some limitation. So 9 to 12% we add MgO along with the, so this MgO, because if you add the dolomite you will get some MgO also. So MgO basically make the slag little thin. We have to do that sometimes because the alumina content, because if the alumina content is little high, I have to add MgO to thin it down. So where the slag get usage, different forms of slag products are produced from the blast furnace slag. Blast furnace slag is very usable. You can have air cooled blast furnace slag. What you do, basically take the slag in a slag pit, you just cool under the normal air, and then you will get a very crystalline solid lump of slag, and then you can crush it, and after that you can use it. It is used basically between the rail sleepers or in the railroad sleepers, you can use it. That is the thing. And then granulated slag is there. Granulated slag is the most important slag that goes to the cement factory. What you do here, you quench the slag very fast using basically the water jet. You can use the water jet and quench it very fast, so fast such that no crystallinity is formed into the slag. It remains completely amorphous and powdery mass, and it has a very cementitious property. That means it absorbs, when it absorbs the water, it becomes hard. So it has, and it is a good substitute into the Portland cement. You can use it. There is the product in non-crystalline powdery solid that exhibit latent hydraulic properties suitable for the cement making, and it goes to the cement plant. So majority of the blast furnace slag goes to the cement plant. And then you have a foamy slag also. If you can control the cooling, not too high, not too low, just making some, because in case of the water jet, instead of water jet, you can mix up the water with some air, and then you can control, and you can form a mist, and then you can cool the slag, and in a controlled fashion, such that your cooling rate is not very high and low, and you can form a slag foam. Slag foam is basically a, you can call it a cellular slag structure, you can make it. And it is used for floor tiles, bricks, building blocks, and all these things. So you have 3 types of slag. One is the air cooled blast furnace slag that can be used, that is very crystalline, hard, and that can be used between the railroad sleepers. That is the major use. Or the granulated slag that goes to the cement plant. It is a powdery, non-crystalline, amorphous slag. And you can also produce the foamy slag by controlling the cooling of the slag. You can make it. Now I come to the blast furnace gas and its usage. It is also very important. And in this slide, basically I have make a comparison of the blast furnace gas with some other useful gases. You can see the type of gases I have given. I have given the blast furnace gas. Analysis is there. That is your how much H2 H2 is 3.7%, hydrogen is unlikely to be less, but if you have some steam injection etc. from there, some H2 is formed. So, H2 is there, and the blast furnace gas, you can see 26 volume percent of blast furnace gas is CO. So, not bad, there is a CO percentage 26%, methane obviously not there, ethane also not there, nitrogen will also be there because our that is the input is air blast. So, nitrogen is around 57% and CO2 obviously 13% is there, and then net calorific value that we get, it is around 3.9 megajoule per meter cube. Okay. Now, we are comparing this blast furnace gas with some other gas. One is called the producer gas, a very important gas. Into the plant you can find producer gas is basically if you burn carbon with air or steam, you can generate some producer gas. So, in this case, you can have hydrogen, 15% hydrogen will be there, because if you use the steam, some hydrogen is also coming. You are basically gasifying the carbon in presence of steam and air. So, you can have some amount of hydrogen, around 15% hydrogen is there, and carbon monoxide is also 24% carbon monoxide is there, and methane, carbon monoxide is there quite, because if you burn the carbon, CO will also come, and if you burn with steam, H2 is also coming, and then you have methane also 2.3% is there, and then your nitrogen is there 52.2% because you use basically the air, and carbon dioxide around 4.8%, oxygen 0.2, and its calorific value is higher than that of the blast furnace gas, 3.9 compared to 3.5.8, but you can understand blast furnace gas is a byproduct of blast furnace operation. Okay, so it is a byproduct gas that also has 3.9 megajoule per meter cube that we can utilize it, but producer gas is produced by gasifying the coal in a separate reactor. Okay. Now, you have a coke oven gas also. Coke oven gas, if you see, it has a hydrogen percentage is quite high in the coke oven gas. This is coke oven gas. How do you get it? Basically, in the coke making process, you have the raw gas, okay, raw volatile, and you process this raw volatile, and then you can get different liquid and solid, liquid and gaseous byproduct. And the major the gaseous byproduct is the coke oven gas, and that is excellent fuel. You can see its net calorific value is 21.5%, very high, and it is also a byproduct. The coke oven byproduct is the coke oven gas. So, and it has hydrogen around 57% hydrogen, and carbon monoxide is 5.9%. and methane is 29.7%. You can see methane is 29.7. Methane is there, quite large amount of methane is there in the coke oven gas because it is coming from the volatile. So, okay. So, methane and ethane is also 1.1, and nitrogen obviously it is unlikely to be there 0.7% because of some air goes in by leakage and all this thing, and CO2 is 1.5, very less. So, it is a very rich gas, rich in hydrogen around 57%, and CO is quite less, 5.9% CO is there, and 57% is the hydrogen in the coke oven gas, and 29% methane is also there. So, it is a very good fuel with a 21.5 megajoule per meter cube of calorific value. And another is called the water gas, or water gas is also called a synthetic gas, and is basically you can get by reforming the hydrocarbons. You can reform the hydrocarbon, basically oxidize the hydrocarbon by carbon dioxide, or you can reform it by steam, basically oxidize by steam. Then you can get a gas that is called the water gas or syngas, and its hydrogen contained is around 50%, 49.7, and CO gas is 39.8, 40% CO, very good. And then methane is 1.3, ethane 0.1, nitrogen 5.5, okay. And then you have CO 3.4, oxygen 0.2, and it has also a very good calorific value 11.4. Okay. And finally, we have the natural gas, that is the only methane. So 94.5 is methane, ethane 0.5, nitrogen 0.4%, and the CO2 0.2, oxygen 0.3. So majority is the methane and nitrogen is there. So it is mostly the fuel is the methane 94.5, and that is why its calorific value is very high, 35.7%. So this is the comparison of blast furnace gas is a byproduct of blast furnace operation, blast furnace gas, and that is 3.9. But here also you note coke oven is also a byproduct gas of coke oven, that calorific value is quite high, 21.5 anyway. So coke oven gas is much more potential than the blast furnace gas, but still the blast furnace gas has a lot of utility. Basically 40% of the blast furnace gas is used for what? 40% is used for your stove, blast furnace stoves, and 60% it goes to the plant for downstream application, and 40% is used in the blast furnace stove. It's self-sustained stove because stove doesn't require any much from other source of fuel. So you can have, so by gasifying the carbon, that is the thing, producer gas, how is produced, as you said, water gas, how it is produced. 40% of the blast furnace gas in the blast furnace stoves, and rest 60% for downstream application in the plant. That is its usage. Okay. So now we talked about the product and their usage, and I will come to some reference. You can go through the book of A.K. Vishwas and then Ghosh Chatterjee and making steel making, and some major conclusions are, first is, as I said, there is a silicon in hot metal can be reduced by low raft and the high top pressure, slag basicity, and the low coal ash, right? But obviously, which is our control? We can control the raft obviously. If you have a very high raft, we can make some water injection or the steam injection, we can reduce the raft. High top pressure, we can use it obviously, and then you can control it. So raft and high top pressure is in our control. Basically, we have to make the hot metal temperature not very high. If it is high, then silicon will go on increasing. That is the major point. Another thing is that by top pressure also we can control it. Basicity, we don't have much to play with the basicity because the operating window, as we have seen, is very narrow, and we cannot go beyond that composition where the basicity is of the order of 1, so we cannot make it 2. Basicity 2 means slag become very viscous and you cannot operate with that slag. And silicon low ash, low coal ash, if you have, then also if you wash the coal and then you can do that thing. So silicon. Now major source sulfur, if you consider, the major source of sulfur in hot metal is the coke ash, and fortunately our coke ash, 90% of the sulfur is come from the coke ash, and fortunately coke ash do not contain too much of sulfur. It is 0.6%. It is the world minimum actually. In coke ash the sulfur percent is minimum. That's why we are fortunate, because we can control the sulfur by basicity to a great extent. Reducing condition in blast furnace is already there, but we using the basicity we can reduce the sulfur significantly, but we do not have much scope, especially for the Indian blast furnace, Indian slag, because of alumina content. We are alumina content in slag is quite harsh, 10 to 22%, as I said. As a result, we cannot make the slag too much of limey, then it becomes very viscous. So with this we can control this sulfur. Hot metal can be produced. That is the 0.04 to 0.5 to 0.08 it can be. And the primary slag with high alumina content in the blast furnace become progressively viscous, okay, until the lime joins the slag and makes it fluid in the boss. As I said, there is the first primary slag forms basically by the constituents of FeO, MnO and your SiO2. They basically form low melting eutectic and alumina, and also alumina is there, low melting eutectic. But after that the primary slag viscosity increases because the FeO content goes down by direct reduction as it moves down, and also by the time lime is also started going in. So if the lime goes into the slag, then it becomes again fluid because glassy substance forms and that's melting fusion temperature is less. So as the lime goes into this slag, it becomes fluid, and finally the slag become fluid after absorbing more lime and the coal ash in the hearth region. And as we have said, This way it progresses. Basically, initially primary slag is FeO L2O3 SiO2 system. It converts to L2O3 SiO2 CO system, right? And then finally this thing. And the operating window of the slag we have seen very narrow, where basicity is of the order of 1. Okay, and the slag can be majority of the blast furnace slag is used into the cement plant, and it is basically called the granulated slag, where it is very amorphous and non-crystalline, and it has a very hydraulic property. What is that called? It has good hydraulic property, latent hydraulic property. That's why it is used into the cement industry. And BF gas is comparatively low calorific value and used into the blast furnace stove as well as downstream application in the plant. Okay, so that's all. Thank you very much for this lecture.